Hello students, in this video we'll discuss geodesic curvature in the geodesic equations. Let's recall, if we're given a curve on a surface, what we can do is we can form the basis, gamma dot, and we can assume that the curve is, of course, an arc length parameter, right? Arc length parameter. What's our gamma dot? And the unit normal vector of the surface, and then n hat cross gamma dot, right? At the basis of three-dimensional space on the surface. Of course, we serve this big configuration, right? We have this idea that here's our surface, right? Here's a curve. Okay, there's my curve gamma. I compute the gamma dot. I compute the normal vector over here, n hat. And then I cross those two things and do n hat cross gamma dot, right? And that's going to go over this direction over here, right? And hit that gamma dot, right? That's right. And so I do this like that. And then the whole idea now is that the second derivative lies in this plane over here, right? The second derivative is somewhere over here, right? Gamma double dot, right? And so we know that gamma double dot is equal to the normal curvature in the direction of n hat plus the geodesic curvature in the direction of n hat cross dot lengths, okay? That's our background information on this. And so now we're going to make a definition. We're going to say definition. Gamma is a geodesic if either gamma double dot is equal to 0, like straight line basically, or gamma double dot is parallel to n hat, right? Okay, that's what it means to be geodesic. In other words, if it's parallel to n hat, there's no KP, right? So an immediate consequence of this stuff. Okay, right? So let's do this consequence. Well, proposition, gamma geodesic if and only if this geodesic curvature is equal to 0, right? Well, from this equation, if its curvature is equal to 0, then you're definitely proportional to n hat. And then if for geodesic, right, then you're parallel to n hat, well, then I know that gamma dot is a unit vector, right? And so gamma dot got the gamma double dot is perpendicular, and you're also perpendicular towards the gamma dot, so you have to be in the direction of n, right? So over that, simple proposition to prove, right? The next proposition we have is the following. So there's a FP vortex. The geodesic be in unit speed parameters array. So that's gamma dot. So we say so gamma must be in unit speed parameterization, right? So if we do derivative, geodesics constant speed. Okay. So if we're going to do, so if it follows with calculation, right? So we know that gamma dot gamma double dot, that's what? Well, gamma double dot is in the direction of the normal vector is equal to 0, right? We look at the overall, that's the fundamental idea, because this is a tangent vector, that's a normal vector. Now, of course, what do we do? If I do the derivative with respect to t, or respect to s, doesn't matter, of gamma dot product gamma dot, what will that be? That's going to be twice gamma dot, gamma double dot, which is 0, right? So in other words, it's a constant here. In other words, this implies that the length of gamma dot squared is a constant. Okay. Give us the left generality, so that was generality so far. Let's do move forward. That gamma unit speed. Great. What I want to do is I want to show that this definition of geodesic, the definition that you're either parallel to your normal vector or you're a straight line, so you're a straight line or you're parallel to a normal vector, if and only if your geodesic curvature is equal to 0. Let's write down equations for these things. This is what happens, okay? So we really have the following. Note that if you're going to be parallel to the if geodesic curvature is equal to 0, parallel to the normal sec. So I can say that the derivative the curve. The curve is going to be what? It's going to be a u dot ru plus v dot rv, because we're on a surface, right? If I dot product this with, for example, ru, that has to be equal to 0, right? That's one. Okay, we go the same with v. A second, right? Now I'm going to do a clever trick with this. The idea, what I'm going to say, this is true if and only if d by dt of u dot, and then ru dot, I'll do the ru dot r. I'll bring the dot product on the inside, which I'm not allowed to do, right? Plus v dot f. That's what happens if I brought the dot product on the inside. So I have to subtract off what? By the product, I have to subtract off the what? The derivative of this here. So that's going to be minus what? Minus u dot ru plus v dot rv. Derivative of ru, derivative of ru going to be, the derivative of ru is going to be what? It's going to be a ruu dot what? Dot u hat, dot u dot, plus ruv dot b dot what? Great. And this 0. Let's wind it over here. Let's look up those expressions over here. So this tells me this is if and only if what? If and only if d by dt of u dot e plus v dot f is equal to what? The minus, of course, minus u dot is u dot squared. Ru dot ruu is the same as the derivative of e with respect to u, but half of them, right? So every example, 1/2 of that's not 1/2 on in front of everything. I'm gonna have an e sub u and then u dot square, right? I'm using the fact here that e, so recall, what am I doing here? I'm saying that e, for example, is ru dot ru, and so if I did an eu, for example, that'd be ru dot ruu times 2, right? By the product rule. And so what that would tell me, that 1/2 of EU is just going to be this expression for it was RUU dot RU. So that's going to be EU with a 1/2. Good. What's the next term we're going to get over here? Well, I have two of these things, right? I'm going to have a RV, RUU, RUV dot R UV, right? So those terms are going to have are going to have 2 u derivatives and 1 b derivative. So that's going to be a what? That's going to be a u derivative of the component over here. So I'm going to have a plus 2 of them, right? So plus 2. And then a what? Plus 2. Oh, so we have this term over here. Yeah, so these terms over here and then these terms over here are both going to give me what? So for example, if we have f, which is ru dot rv, if I need a u derivative of f sub u would be ruu dot rv, and then plus what? Plus ruv, right? And then by the symmetry of the dot product, I can pass those things onto the other one over here. So each of these expressions over here are going to be f sub u 2, right? So 2 f sub u, u dot v dot, and then finally plus, if I have a ruv, that's the 1/2 the u derivative, g, right? That's going to be a g u v dot squared. So that's my first derivative equals 0, right? If I exacted the analogous trees, we're going to get the following. I'm going to have d by dt, with the other equation. If I replace this u over here, so let's do it like this. So let's do it like this. If I replace this u over here, where's the power? If I do this with dot rv, I'm gonna get the same exact relationships equal to 0. But what's the silly modification? All the u derivatives are going to turn to be derivative, right? So this is d by dt of u dot f plus v dot g. I'm shifting them over. Minus 1/2 e v u dot squared plus 2 f v u dot v dot plus g v v dot squared is equal to 0. And these two equations over here are a system of second-order differential equations. And so these are Geodesic equations. And we've previously shown that geodesic equations are the ones that locally minimize the distance between 2 points on the surface. So these are going to locally minimize some trajectories, locally minimize. Of course, they're nonlinear ODEs, right? Locally minimize distance on the surface. Okay, and so that basically ties down together this idea of we've already deriven the geodesic equations from the Euler-Lagrange equations in the previous video, right? So that derivation with Euler-Lagrange gives us a system of nonlinear system of 2 second-order differential equations, and that's exactly the same form we have over here. So by taking that proof and feeding it into this juncture, feeding it back up to this juncture shows that you're geodesic, that you're locally minimizing distances on F, if and only if your geodesic curvature is equal to 0. Thank you very much.